Welcome back to Miss Graham's Maths. This video is looking at the worked solutions for probability concepts, standard 91585 from the D&D Resources practice assessment. So this is practice external assessment number 6 from their booklet. So first of all, a thank you to D&D Resources for allowing me to use their materials in this way. I have put a link to their website where you can order these books online. I highly recommend that you get yourself a paper copy and use them as practice for the real exams, giving yourself as much of that experience as possible of putting pen to paper. Okay, on to question 1. We're starting with some information about vehicle crashes and how bad the injuries were from those crashes. For year 1, 2 and 3, we're looking at which one has the lowest overall risk of a serious injury. So that's this line just here. Risks for those was year 1 is 1,717 out of 32,334 crashes. So that's a 0.0531 chance of those crashes being resulting in serious injury. Year 2 is 1730 out of 30,339. Not 0.05702, and year 3 is 1653 out of 29970. Not 0.0552. Year 1 is the lowest risk. All right, give one reason why the risks you calculated for years 1 to 3 are likely to be estimates only. So let's take another look back at the information. This was the number of motor vehicle crashes reported to the New Zealand police over these 3 periods and their seriousness. So this is important that it's the ones that are reported to the police, and not all accidents would be reported to the police, especially if it didn't result in injury or the injury was quite minor. So I'll write something about that. Okay, a driver wants to estimate his risk in a future year of having a motor vehicle crash involving serious injury in New Zealand based on these statistics. Comment on 2 factors the driver should consider when estimating his future risk. So the first thing that I've put is along the lines of, we've got this data about like a large group of people, but he is trying to estimate it for one particular person, and he needs to consider the characteristics that might affect his own risk, such as his own age, his driving experience, the type of driving he does, whether he does a lot of driving at night, for example, or if it's in city traffic, or if it's on rural roads, etc. And the other thing, I just scrolled back up to the question just up here to see what we've got for the source. All we've got is that it's the source from the Ministry of Transport, but we don't know when this information was from. So the second reason that I've put down here, well, second factor, is that we don't know when this data is from. Each year of those risks that we just worked out was slightly different, so he should make sure he has the most recent data to see if anything has changed before he uses it. Okay, now let's determine the probability that a random accident within this period involved minor injury only and occurred in year 2. So minor injury and year 2. Let's take a look back at our numbers. So minor injury in year 2 is 7607. And the total number of accidents we have here is 32334 plus 30339, 29970. So this is going to be 7607 out of our total. So it's 0.08211. Now, I have done this question slightly differently to the answers in the back of the book, and that's all down to the wording of the question. I think it's a minor error in the way that the answers in the book have been done because of the wording, and I'll just explain that now. So in our question, we've got to determine the probability that the random accident in this period of time involved minor injury only and occurred in year 12. In year 2. So that there is our whole thing that makes this thing here. If it was going to be a conditional probability, like it shows in the answer book where it says year 2, given that it's a minor injury, the wording would need to be slightly different. It would say determine the probability that a random accident picked in this time period that just here, so that involved minor injury only had occurred in year 2. So that's setting up a condition first, whereas the question as it's printed is actually saying that we want to pick one that just involved minor injury and it occurred in year 2. This question has not been written to provide a conditional probability, which is why I slightly disagree with the answer that's in the book and think you should do it in this pink way. Okay, moving on to the next one. 3 accidents chosen at random. Calculate the probability that 2 of them involved minor injury only. So if we're picking 3, we want 2 to fit our category. We could have the first 2 fit it, and then the last one doesn't. We could have yes, no, yes, or no, yes, yes, and we'll work out the probabilities. So involving a minor injury only. Let's take a look back at our table. So we need to add these ones up. So 7828, 7607, and 7456 makes a total of 22891. So the chance of picking one of those is 22891 out of our total number of accidents, 92643. If we've taken one of those out, we'll then have 22890 left out of 92642. And then if we do a subtraction to find out everything else, so 92643 take away 22891 means there are 69,752 accidents that weren't minor injury only. So now we have that many left out of the total we've now got after we've picked 2 of them out. So that's going to be like this. Now, the probability, we'll need to do that times by 3 because we've got these 3 different ways that we could do that thing, and they'll come out to the same answer, each of them. Okay, I'm going to pause this, pop it into the calculator to get the answer. We have 0.1379. All right, question 2. Jacob's got a minibus with 8 seats. 10% of the people who book seats don't show up, so Jacob always sells 10 tickets for each of the trips that he makes. And then we've got this table of information of the last 30 trips that he did. So the top line is each of these, like, think of this table in 2 halves. So the top half and the bottom half are showing the 30 lots of things. It would help if there was a gap between them, but this solid line here is separating the 2 lots of 15. Okay, what proportion of the last 30 trips did not have enough seats for the number of people who actually turned up? So we're looking for where the people who turned up exceeded the 8 seats that he's got in the minibus. So that would happen on these ones here. And there's 21 of those, so it's 21 out of 30, which is 70%. Okay, now what's the theoretical probability that all 10 people that booked would turn up? Let's go back to the information here. We've got 10% of the people who book seats don't show up. So we've got a chance of each one showing up is 0.9. So the first person showing up is 0.9, the second person 0.9, and so on until we've done 10 of those for the 10 people. So all 10 people showed up would be 0.9 to the power of 10. So that is 0.3487. Then state any assumption we've made, which is independence here. Now, in reality, that's not likely to be the case because you might have people that are booking together. So if one wasn't going to turn up, it would impact the other person turning up or not turning up. But that's all we need to put for this question. Okay, Jacob now decides to conduct a simulation to investigate the variability in the number of people who turn up after booking a seat. And then we've got the summary of that simulation on this table. Okay, so is Jacob's strategy of selling 10 seats for each of the trips a good one? So I'm going to start by looking at where he would get into trouble with that method, and that's when too many people turn up, when we've got 9 or 10 people turn up. So the probability of not enough seats is going to be 192 plus 177 out of our total of 500 trials. It's quite a lot. So let's do this now. 0.738. So 74% of the time, he's going to have to tell people that he can't take them when they've booked. That's not good for his business. The other way we could support this reasoning is if we get the expected number of people turning up, and I'm just going across to, I meant to go to the stats menu here. We can put these numbers in to our table and it can give us the expected amount. I haven't bothered putting in the 0 to 4 people because that would be times by 0. So we had 2, 8, 23, 98, 192 and 177. Now the calculator can work out the expected number of people to turn up. We just need to tell it that the frequency is sitting there in list 2. So if we go to calculate and in our settings on F6, we've got the thing that we have listed as X in list 1, that's correct. But the frequency, we go to the F2 button and tell it that it's in list 2. Okay, now we go to one variable calculations and it tells us that the expected value here is represented by X bar, so that's a 9. So that would exceed the number of seats he's got available by a whole person. It's not just a little bit over over 8. So it's not a good method to use. For this information here, we've got two types of information: their age and how they paid. So we can pop this into a two-way table. So the age, we can have those that were under 50, those that were over 50. So I just paused for a sec to think where the 50 gets included. So we've got over 50 as being categorized for us. So the other one would be less than or equal to 50. And then total. Paid by direct credit and paid by credit card. And then total. Okay, 22 people were over 50 and paid by credit card. 72 paid by direct credit. 65 were aged 50 or less. And we've got 120 in total. So 120 minus 72 gives us a 48 here. 65 minus, 120 minus 65 gives us a 55 here. 55 take off 22 gives us 33 just there. 72 minus 33 is 39, and 48 minus 22 is 26, and I'll just check 39 plus 26 adds to 65 to make sure I haven't made any mistakes. Now, if two people were selected at random from this sample, calculate the probability that they both used a credit card for payment. So if we pick out the first person, so both credit card, the chance of picking the first person and being credit card would be 48 out of 120. Now we've removed them from the pot, we would have 47 left out of 119. Which is a 0.158. Part 2, we're checking for independence. For this one, we're checking if the probability of A times the probability of B is equal to the probability of A and B. Okay, so A is paid by credit card. So chance of paying by credit card is 48 out of 120. B is 50 or less, so they are 65 out of 120. And then both paid by credit card and 50 or less is 26 out of 120. So let's test this out, times them together. That's equal to 13 over 60, which is the same as 26 over 120. So therefore, the probability of A times the probability of B is equal to the probability of A and B. And if that's true, it means they're independent. Now, one final part, always make sure we've answered the question. Explain what that means in the context of this question. And that is that a person's age, so the category of age they were put in, does not have an impact on the likelihood of the way that they choose to pay. Question 3, we're looking at the sources of bookings, so over the phone, online, or via his website, or walk-ins to the depot. So we've got 3 types: phone, online, walk-in. 74% of the bookings are by the website, 6% are walk-ins. And then we've got the chance of them showing up. We want to work out, do Jacob's figures support his belief that 10% of the people who book seats don't show up? So we want to work out what's the chance of them not showing up. Okay, so we could book by phone, online, or walk-in, and the chance of that is, of each of those, we've got 75% of the bookings are on the website, so that's 0.74. We've got walk-ins are 6%. Oh, sorry, I should have put the 0.74 here for online, and W is for walk-in. I'm just going to put that. Phone. Okay, there we go. So 74 plus 6 would be 80. That leaves us with a 0.2 for phone bookings. Now, successful, meaning they turn up. So we'll have successful, not successful. So this is 0.92. This is 0.08 for... I've done it again, I've put it on the wrong branch, hold on. For the phone bookings, it's 0.85 success, 0.15 not successful. For the online ones, we have 0.92 success and 0.08 not successful. And for the walk-ins, we got 0.82 for success and 0.18 for not successful. Okay, so the probability of getting an unsuccessful booking is going to be all the branches that end in not success. So 0.2 times 0.15, 0.74 times 0.08, and 0.06 times 0.18. This is 0.1. That's equal to 10%, so it does support his belief. Of the successful bookings where a person shows up, what's the proportion that were from the website? So this is a conditional probability. So given that it was a successful booking, what's the probability that it was booked online? So that's the probability of it being online and successful divided by the probability of it being successful. So online and successful is 0.74 times by 0.92. And it's divided by the successful ones. Well, we just found out that not successful was 10%, so successful would be 0.9. Which comes to 0.7564. Now, of the three types of bookings, which of those exposes Jacob to the greatest risk of people not showing up? And it's given us a hint to assume that Jacob received 1,000 bookings and use that to work out what numbers. So if we have a total of 1,000 bookings that were booked, what were our options again? We had phone, online, and walk-in. So phone, online, walk-in. Now assume we have a total of 1,000 people and then they were successful or not successful. Often it's easier to see what we're doing if we pop some numbers in like this rather than dealing with the probabilities directly. So if we've got 1,000 people and we've got 20% are on the phone, 74% are online, and 6% are walk-in. So 20%, 0.2 times 1,000 would give us 200 people that booked on the phone. 74% is going to be, I realise I'm doing something on a calculator. It would be very easy to do anyway. So 740 for online and 60 for walk-in. We just worked out that the chance of them not showing up was 10%. So 10% of 1,000 is 100. So 900 of them would be successful. Now let's work out what we've got for each of phone, online, and walk-in. So of the phone ones, 85% of those are successful. Okay, so 85% of 200 are successful. So we have 170 in here, and that would leave 30 here. Online, 92% of those are successful. I'm just looking at this bit here. And walk-ins, 82% were successful. So 92 and 82. There we go. So 0.92 of 740. We'll round that to 681. And 0.82 of 60. We'll round to 49. Okay, and then the leftover piece is 740 minus 681 is 59, and 60 minus 49 is 11. Right, so the probability that they don't show up if they booked on the phone is 30 out of 200. 0.15. Probability they don't show up if they booked online is 59 out of 740. and the probability of them not showing up if they were a walk-in is 11 out of 60. So walk-ins have the greatest risk of not showing up. Now in the question it asked us to work out appropriate comparative risk statements. So we need to say how many times more risky they are. And we'll do it by comparing it to the least risky one here. So if we do the 0.183 divided by 79 over, oh sorry, it's not 79, it's 59 out of 740, we can see it's 2.3 times as likely. We'll do the same with the phone bookings. So 0.15 divided by the online risk makes them 1.88 times as likely compared to the online bookings. All right, for this last one, we've got 2 bookings made. The first is by the website, the second is by phone. Calculate the probability only one of the bookings is successful. So that could be we have the online booking is successful and the phone booking not successful, or online not successful and the phone is successful. Just writing these kind of shorthand at the moment. Okay, so now let's work those things out. So we want the probability of online and success and phone and not success. Okay, so online and successful. Let's go back up here. Where did we have that tree diagram? So online and successful, 0.74 times 0.92. Actually, I'm going to grab that tree diagram and bring it down here. There we go. So we've got online and successful, 0.74 times 0.92. And then the second one, phone and success, not successful, is 0.2 times 0.15. So that's 0.020424. Okay, then the other way round of doing it is that we have online not successful and phone is successful. So that's 0.74 times 0.08 times phone is 0.2 times 0.85, making 0.010064. Okay, now let's add them together. And we've got that probability. It's tempting to think that that is done, but we actually have a conditional situation here. So if the first booking is done like this, the first booking is by the website and the second is by a phone booking. So we're applying that condition as well. So we need to put this as a conditional probability. So getting one success given that they booked by doing online and then the phone. So one success is 0.0030488 out of the chance that they booked online and then by the phone. Well, online is 0.74 and then followed by the phone is 0.2. That makes us a 0.148 on the bottom. So let's go 0.030488 divided by 0.148, which is 0.206. Now, that was a pretty tricky one. There were lots of places you could go wrong with that, or stop before you'd actually finished. But yeah, hopefully you've been able to follow that through, and the color coding helps to pick out the different pieces. Okay, that brings us to the end of the probability concepts papers from the D&D Resources. If you found this helpful, please interact with the video, like, subscribe, comment, whatever, because it helps other people to find their way here too, and they'll probably find it useful if you did. If you're looking for more help, there's more that you can find through my homepage. There's video tutorials, there's more worked solution videos on the D&D stuff, there's worked solutions for and video walkthroughs of past papers. So go take a look and see what else you'll find helpful as well, and I'll see you next time.